Look up at the night sky for a moment. It feels calm, silent, unchanging. The stars seem fixed in place, just as they did for people thousands of years ago. For most of human history, we believed the universe was like this forever. Always there, always steady. A giant, quiet stage where nothing truly changes on the biggest scale. But here is the mystery that changes everything. The universe is not calm, it is not still, it is expanding. And even more shocking, that expansion is speeding up. This is not a small detail hidden in textbooks. This is one of the biggest discoveries in modern science. Galaxies are moving away from each other. Space itself is stretching. And the farther we look, the faster everything seems to be running away. Imagine dots painted on a balloon. As the balloon inflates, every dot moves away from every other dot. That is close to what is happening to our universe. But there is a twist. The balloon is not inflating at a steady speed. It is inflating faster and faster with time. That single fact breaks our everyday intuition. If you throw a ball into the air, gravity slows it down. If you roll a bicycle uphill, it loses speed. Gravity is a pulling force. It brings things together. So if the universe began with an explosion, as the Big Bang Theory says, gravity should slowly pull everything back. Expansion should be slowing down. That was the expectation, that was the safe idea. That was the idea most scientists believed for decades. But the universe did not listen. Instead of slowing down, the expansion is accelerating. Something is pushing space apart. Something powerful, invisible, and deeply mysterious fills the universe and overwhelms gravity on the largest scales. Scientists gave it a simple name, not because they understand it, but because they do not. They call it dark energy. Dark energy is not something you can touch. You cannot see it with a telescope. You cannot bottle it in a lab. It does not glow, it does not reflect light, and it does not behave like anything we experience in daily life. Yet it dominates the universe. Roughly 70% of everything that exists is controlled by this strange energy. Galaxies, stars, planets, and even us are just a small minority of the cosmic budget. Now here is where the story becomes truly surprising. Long before dark energy was discovered, long before anyone even imagined that space itself could push outward, long before modern telescopes and space observatories, one man wrote down equations that seemed to describe this very behavior, and he did it for an entirely different reason. That man was Albert Einstein. Einstein is often remembered as the genius who unlocked the secrets of time and space. The man who showed us that time can slow down, space can bend, and gravity is not just a force but a shape. But Einstein was also human. He had assumptions. He had preferences. He believed, like almost everyone else in his time, that the universe was static, eternal, unchanging, on the largest scale. When Einstein applied his revolutionary theory of gravity to the entire universe, something uncomfortable appeared. His equations did not want a still universe. They naturally predicted a universe that expands or collapses. That result bothered him deeply. It did not match the accepted picture of the cosmos. So Einstein did something that scientists sometimes do when theory and belief collide. He adjusted the equation. He added a new term, a small mathematical ingredient designed to balance gravity, a kind of cosmic counterforce. Its job was simple: keep the universe from moving, keep it stable, keep it calm. At the time, it seemed reasonable, elegant even. Just a minor correction to make the math fit reality as it was understood. That term became known as the cosmological constant. Decades later, when astronomers discovered that the universe is expanding, Einstein reportedly called this addition his biggest mistake. The cosmological constant seemed unnecessary. Gravity alone was enough to describe an expanding universe, or so it appeared, but the story did not end there. When scientists discovered that expansion is accelerating, they went back to Einstein's equations, and waiting there, quietly, was the cosmological constant. The the same term Einstein once introduced to freeze the universe, the same term he later regretted. Now it looked suspiciously like dark energy. This raises a breathtaking question. Did Einstein accidentally predict dark energy? Did he unknowingly write down the mathematics of a force that humanity would only discover many decades later? Or is this just a coincidence, a lucky overlap between equations and observation? This question is not about proving Einstein right or wrong. That is too simple. Science is not a courtroom. It is a conversation with reality. Sometimes reality answers in ways we do not expect. Sometimes it whispers. Sometimes it shouts. And sometimes it waits patiently for us to catch up. The idea that a mistake could become a prediction is not as strange as it sounds. In science, equations often know more than the people who write them. Mathematics has a way of revealing truths before our minds are ready to accept them. Many discoveries began as unwanted results, ignored terms, or uncomfortable conclusions. Dark energy is one of those discoveries that forces humility. We use it every time we describe the universe, yet we do not truly understand what it is. We can measure its effects, but not its nature. We can see its influence, but not its source. It is a reminder that knowledge does not arrive all at once. It comes in pieces, sometimes centuries apart. This story is also a reminder that genius does not mean certainty. Einstein was brilliant, but he was not all-knowing. He doubted quantum mechanics. He resisted randomness. He preferred a universe that made intuitive sense. And yet, some of his greatest contributions came from equations that went beyond his personal beliefs. In this journey, we are not hunting for heroes or villains. We are not rewriting history to flatter or criticize one man. We are following an idea as it travels through time, from chalkboards covered in symbols, to telescopes scanning distant galaxies, to modern scientists trying to understand why empty space has power. We will move slowly, step by step. We will avoid heavy math. We will focus on meaning, not formulas. We will see how a simple assumption about a still universe led to one of the deepest mysteries in modern cosmology. We will see how observation humbled theory, and how theory, in turn, guided observation. By the end of this journey, the question may look different. It may no longer be about whether Einstein predicted dark energy by accident. It may become a question about how science really works, about how ideas evolve, about how the universe refuses to fit neatly into our expectations. Because the universe does not care what we prefer. It expands when we expect stillness. It accelerates when we expect slowing. And sometimes it hides its greatest secrets inside equations written long before we know how to read them. This is the story of that mystery, from a universe that should have slowed down, to a force that pushes everything apart, from a simple mathematical fix to the dominant energy of the cosmos. This is not the story of being right or wrong. This is the story of being surprised, and it begins with one simple, unsettling fact. The universe is running away from us faster than ever. To understand how dark energy could even be connected to Einstein, we first need to step back in time. Not just a few years, but more than a century, to a world where the universe felt much smaller, calmer, and far more certain than it does today. This was the scientific world of the early 1900s, the world in which Albert Einstein was thinking, calculating, and reshaping physics from the ground up. At that time, the universe was not seen as a place of drama and motion. There was no talk of expanding space, accelerating galaxies, or mysterious energies filling the void. The universe was believed to be static, eternal, always the same on the largest scale. Stars might move slightly, nebulae might shift, but the overall structure of the cosmos was assumed to be fixed, like a grand painting hanging forever in the background of reality. This belief was not foolish or unscientific. It was the most reasonable conclusion based on what people could observe. telescopes were limited. Most astronomers believed that the Milky Way galaxy was the entire universe. The faint, fuzzy smudges seen in the sky were thought to be small gas clouds inside our own galaxy, not distant galaxies of their own. Without evidence of large-scale motion, stillness felt natural. Philosophy also played a role. Many scientists were influenced by the idea of an eternal universe, one with no beginning and no end, a universe that simply exists, without creation or collapse. This idea, elegant and safe, a universe that changes dramatically, raises uncomfortable questions. Where did it come from? Why does it evolve? Does it have an end? These questions blurred the line between physics and philosophy, something many scientists preferred to avoid. Einstein himself was deeply shaped by this environment. Although he was revolutionary in his thinking about space and time, he was surprisingly conservative when it came to the universe as a whole. He did not imagine a cosmos that expanded or contracted. He imagined one that simply was. When Einstein completed his theory of general relativity in 1915, he had created something astonishing. A new description of gravity, not as a force pulling objects together, but as the bending of space and time by mass and energy. This theory worked beautifully for planets, stars, and light. It explained strange effects that Newton's gravity could not. It passed every test thrown at it. Naturally, Einstein wondered what would happen if he applied these equations to the entire universe. What does gravity look like on the biggest possible scale? What shape does space itself take when all matter is included? This is where the discomfort began. When Einstein used his equations to describe the universe as a whole, they did not allow a static solution. The mathematics insisted on change. Either the universe must be expanding or it must be collapsing. There was no option for perfect stillness. This result came directly from the equations themselves, not from observation. For Einstein, this was a problem, not because the math was wrong, but because the result clashed with everything scientists believed at the time. A dynamic universe felt radical, almost reckless. There was no observational evidence to support it. No astronomer was claiming that galaxies were rushing away from each other. No data suggested that space itself could stretch. In the scientific culture of the early 20th century, observations were important, but they were also limited. Telescopes could only see so far. Measurements were uncertain. The universe beyond the Milky Way was a mystery. In that environment, theoretical consistency often carried more weight than incomplete data. Einstein trusted mathematics deeply. To him, equations were not just tools, they were windows into reality. He believed that if the math was elegant and internally consistent, it was likely pointing toward truth. But he also believed that nature should make sense, not shock us unnecessarily. So when his equations produced an expanding or collapsing universe, Einstein did not immediately embrace the idea. Instead, he searched for balance. He looked for a way to keep the universe stable without breaking the mathematics. This decision makes more sense when we remember the mindset of the era. Science was not yet a story of violent beginnings and dramatic endings. There was no Big Bang theory, no cosmic timeline. The universe was thought of as timeless. Introducing motion on a cosmic scale felt like opening a door to chaos. There was also a psychological element. Einstein had just overturned centuries of understanding about space and time. His theory was already difficult, abstract, and controversial. Proposing that the entire universe was in motion might have felt like pushing too far, too fast. So he chose caution. By adding a small term to his equations, Einstein could counteract gravity on large scales. This new term acted like a gentle repulsion, preventing the universe from collapsing inward. With this adjustment, the universe could remain static, balanced perfectly between attraction and repulsion. Calm once again. At the time, this was not seen as a mistake. It was seen as a reasonable solution. Many great physicists modify equations to match reality as it is understood. Einstein was not forcing the universe to behave unnaturally. He was aligning his theory with the accepted picture of the cosmos. What is striking, in hindsight, is not that Einstein believed in a static universe. Almost everyone did. What is striking is that his equations already contained the seed of something far more dramatic, a universe that changes, a universe that evolves, a universe that refuses to stay still. But that interpretation would take years to emerge. In the early 1900s, cosmology was not even a well-defined field. Physics focused on atoms, light, and energy. Astronomy focused on stars and planets. The idea of studying the universe as a single physical system was still new and uncertain. Einstein was one of the first people to seriously attempt it. Because of this, he relied more on theory than observation. Observational cosmology was simply not mature enough to guide him. When data is scarce, theory becomes the compass. And Einstein's compass pointed toward mathematical elegance and philosophical comfort. This helps us understand why the idea of a changing universe felt so uncomfortable. Change implies history. History implies a beginning. And beginnings raise questions science was not yet prepared to answer. A static universe avoids all of that. It is also important to remember that Einstein was not arrogant. He did not believe his intuition was infallible. He believed in coherence, in harmony between equations and worldview. When those clashed, he adjusted the equations in the least disruptive way possible. From today's perspective, it is easy to say he should have trusted the original equations and accepted expansion immediately. But that judgment uses a century of hindsight. At the time, doing so would have felt like speculation without evidence. Einstein's universe in the early 1900s was calm, eternal, and balanced. It was a universe that matched human expectation and philosophical tradition. A universe that did not surprise you in the middle of the night. Dark energy did not exist as a concept. Accelerating expansion was unimaginable. Empty space was thought to be empty, not powerful. The idea that nothing could push something apart would have sounded absurd. And yet, hidden inside Einstein's work was a mathematical whisper, a suggestion that space itself might have energy, that emptiness might not be empty, that the universe might be far stranger than even a genius was ready to accept. At this stage of the story, Einstein was not predicting dark energy. He was trying to avoid a moving universe, but in doing so, he left behind a clue, a term in an equation, a quiet possibility waiting for a future generation to notice. This is what makes the story so compelling. Dark energy did not emerge from wild imagination. It emerged from restraint, from caution, from an attempt to keep the universe simple. Before dark energy existed, before expansion was observed, before cosmology became a science of motion, Einstein stood at the edge of a truth he did not yet want to face, and the universe waited. To understand how dark energy could hide inside Einstein's work, we first need to understand the idea that made everything possible. General relativity. This is not just another theory in physics, it is a completely new way of seeing reality. Before it, gravity was thought of as a force, something invisible that pulls objects together across empty space. After it, gravity became something far stranger and far more beautiful. When Albert Einstein introduced general relativity in 1915, he was not trying to explain the universe. He was trying to understand gravity at its deepest level. Why do apples fall? Why do planets orbit stars? Why does light bend near massive objects? Newton's laws worked well, but Einstein felt they were incomplete. They described how gravity behaves, not what gravity truly is. Einstein's answer was radical. Gravity is not a force pulling things together. Gravity is the shape of space and time itself. To make this idea intuitive, imagine space and time as a single fabric, often called space-time. This fabric is not rigid. It can stretch, bend, and curve. When you place a massive object, like a star or a planet, onto this fabric, it creates a dent. Smaller objects move along the curves created by that dent. They are not being pulled by an invisible rope. They are simply following the natural shape of space-time. This is why planets orbit stars. This is why light bends near massive galaxies. Even light, which has no mass, follows the curves of space-time. Gravity, in Einstein's view, is geometry. What makes this idea so powerful is that it applies everywhere, not just on Earth, not just in our solar system. Einstein's equations do not care whether they are describing a falling apple or an entire galaxy. They describe how space-time responds to mass and energy, no matter the scale. This is why general relativity naturally extends to the entire universe. If space-time can curve around a planet, it can also curve on cosmic scales. If matter tells space-time how to bend locally, then all matter combined tells space-time how to behave. Globally, this was a revolutionary leap. For the first time, scientists had equations that could describe the universe as a whole, not just objects inside it. Space itself became a dynamic player in the story, not a passive background. And this is where things get interesting. Einstein's equations are not just descriptions, they are predictions. They tell space-time how to behave under different conditions. And sometimes, they predict things long before humans observe them. For example, general relativity predicted that light would bend near massive objects. This was confirmed years later during a solar eclipse. It predicted black holes before anyone believed they could exist. It predicted gravitational waves, ripples in space-time itself, which were detected a century later. In each case, the equation spoke first and observation followed. This pattern matters deeply for the story of dark energy. When Einstein wrote his equations, he did not insert expansion or contraction by hand. The equations naturally allowed space-time to change, to stretch, to shrink, to evolve. In other words, general relativity does not prefer a static universe. It prefers a dynamic one. This is not because Einstein wanted change. It is because the mathematics demands it. When you apply general relativity to a universe filled with matter and energy, space-time cannot remain perfectly still. It must respond. Think of space-time as a flexible sheet under tension. Fill it with matter, and it will move. Hold it perfectly still, and you must add something extra to counterbalance that motion. This is exactly the problem Einstein faced. His equations were telling him something uncomfortable. They were saying that the universe could not simply sit there forever. It must either expand outward or collapse inward. There was no stable middle ground. This was not speculation. It was a direct consequence of the theory. What makes this so important is that Einstein trusted these equations more than intuition. He believed that nature follows deep mathematical principles, even when they conflict with common sense. This belief guided much of his work. But even Einstein had limits. At the time, there was no observational evidence that the universe was expanding. None. Accepting expansion would have meant trusting mathematics over every telescope on Earth. That was a bold step, even for him. So instead of rejecting the equations, Einstein adjusted them. He added a term that acted like an internal pressure of space itself, a way to balance gravity and keep space-time stable on the largest scales. This addition did not break the theory. It fit naturally within the mathematics. In fact, it was allowed by the structure of the equations. It was not a hack. It was a legitimate possibility. This is a crucial point. The cosmological constant was not an error in math. It was a choice in interpretation. General relativity is flexible. It allows different solutions depending on what fills the universe. Matter curves space-time inward. Energy can curve it outward. Empty space, surprisingly, does not have to be neutral. It can have properties of its own. This idea was deeply counterintuitive at the time. Space was thought of as nothing, a stage where physics happens. Einstein's equations suggested something else. That space itself might carry energy. That emptiness might have weight, pressure, and influence. Einstein himself did not fully explore this implication. His focus was balance, not acceleration. But the door was open. This is why general relativity matters so much for dark energy. Dark energy is not an external force added to physics. It fits naturally into Einstein's framework. It behaves like an energy of space itself, a property of the vacuum. In simple terms, if space-time has energy, then as space expands, more of this energy appears. More space means more push, and that push accelerates expansion even further. This creates a runaway effect. Nothing in Newton's gravity allows this. Only general relativity does. This also explains why dark energy only becomes important on large scales. On Earth, gravity dominates. In galaxies, gravity still wins. But across billions of light years, the subtle energy of space itself begins to take over. Einstein's equations describe all of this without ever mentioning dark energy by name. They describe how space-time responds to whatever fills it. If that filling includes a mysterious energy of empty space, the equations accept it without complaint. This is the strange power of mathematics in physics. It does not care about human comfort. It does not care about expectation. It simply follows logic to its conclusion. Many of the most profound discoveries in science began this way. An equation predicts something odd. Scientists ignore it. Then reality catches up. In the case of general relativity, the equations quietly allowed for expanding space, accelerating space, and energy embedded in the vacuum, all long before telescopes confirmed any of it. This does not mean Einstein secretly knew about dark energy. It means he built a framework broad enough to contain truths he did not yet imagine. That is the difference between a clever model and a deep theory. A model fits known data. A deep theory reveals new possibilities. General relativity changed reality, not because it answered every question, but because it changed what questions could even be asked. It turned space from a passive background into an active participant. It turned gravity from a force into geometry, and it made the universe itself a dynamic object, capable of growth, motion, and surprise. Without general relativity, dark energy would make no sense. There would be no place for it, no language to describe it, no equation to hold it. The mystery of dark energy is not separate from Einstein's work. It lives inside it. When people hear the phrase cosmological constant, it often sounds intimidating, like a piece of advanced mathematics meant only for physicists. But at its heart, the idea is surprisingly simple. It began as an attempt to keep the universe calm. To see why this mattered so much, we need to return to the moment when Albert Einstein first applied his theory of general relativity to the universe as a whole. His equations were powerful. They described how mass and energy bend space and time. They worked beautifully for planets, stars, and light. But when Einstein used them on the largest possible scale, something troubling happened. The equations refused to produce a universe that simply sits there. Instead, they predicted motion. Either everything must be moving closer together, collapsing inward under gravity, or everything must be moving apart, expanding into space. There was no stable option, no peaceful middle ground. The universe, according to the math, could not be eternal and still. This result clashed sharply with the scientific belief of the time. In the early 1900s, almost everyone assumed the universe was static and eternal. There was no evidence for expansion. No observation suggested large-scale motion. Accepting a changing universe would have meant trusting theory over every telescope available. Einstein faced a choice. He could accept what his equations were telling him, even though it contradicted accepted belief, or he could modify the equations in a small, careful way to restore balance. He chose balance. The cosmological constant was that choice. In plain language, the cosmological constant is a term that represents a built-in energy of space itself. Not energy in stars or matter, but energy that belongs to empty space. This energy creates a gentle outward push, a repulsion that works against gravity. Gravity pulls matter together. The cosmological constant pushes space apart. Einstein added this term to his equations to do one very specific job. It was meant to exactly counteract gravity on the largest scales. If gravity tried to pull the universe inward, this new term would push outward just enough to stop collapse. The result would be a universe that remains perfectly balanced, neither expanding nor contracting, just existing. It is important to understand that Einstein did not see this as cheating. His equations allowed this term naturally. The mathematics of general relativity does not forbid energy in empty space. In fact, it quietly permits it. The cosmological constant fit neatly into the structure of the theory. Think of it like tuning a scale. On one side, you place gravity. On the other side, you place a small amount of repulsion. When the two forces match, the scale stays level. That level state was Einstein's static universe. This idea felt elegant at the time. It preserved the accepted picture of the cosmos while keeping the theory mathematically consistent. Einstein believed he had solved a problem, not created one. What makes this story fascinating is how subtle the cosmological constant is. It does not dominate on small scales. It does not affect how apples fall or how planets orbit. On Earth, gravity is far stronger. Even in galaxies, gravity wins. The cosmological constant only becomes important when you consider the universe as a whole. This made it easy to overlook, easy to dismiss, easy to forget. For years, that is exactly what happened. But let's pause and really understand what Einstein had done, even if he did not fully realize it. By adding the cosmological constant, he was saying something radical. He was saying that empty space is not truly empty. That space itself can have energy, that nothingness can push. At the time, this idea was deeply uncomfortable. Space was traditionally seen as a stage, not an actor. Physics happened in space, but space itself did not do anything. Einstein's equations suggested otherwise. The cosmological constant turned space into an active participant, a substance with properties, a thing that could influence the fate of the universe. Even though Einstein's goal was stability, the implication was far broader. If space has energy, then the behavior of the universe depends not just on matter and radiation, but on space itself. This is why the cosmological constant would later become legendary. When astronomers eventually discovered that the universe is expanding, Einstein's static model collapsed. The need for a balancing term seemed to disappear. Gravity alone could describe an expanding universe. The cosmological constant looked unnecessary, even embarrassing. Einstein reportedly regretted adding it. He believed he had forced the universe to behave according to expectation rather than listening fully to the equations. Whether or not he truly called it his biggest blunder, the sentiment captured something real. The constant seemed like an artificial fix. For a while, scientists removed it from their equations and moved on. But the universe was not done surprising us. When observations revealed that expansion is accelerating, gravity alone was no longer enough. Something had to be pushing space apart. Something that acts everywhere, all the time, growing stronger as space grows larger. Suddenly, the cosmological constant made sense again. That small term Einstein added for the wrong reason behaved exactly like the mysterious force driving acceleration. It acted like a constant energy density of space. It produced a steady outward push. It did not dilute as the universe expanded. In fact, as space increased, so did its total influence. This is what makes the cosmological constant so powerful. Matter spreads out as the universe expands. Radiation weakens. Gravity's pull fades over large distances. But a constant energy of space does not thin out. It remains the same everywhere. As the universe grows, gravity loses its grip. The cosmological constant does not. Eventually, it dominates. Einstein never imagined this outcome. His goal was stillness, not acceleration. But the mathematics did not care about intention. It cared about consistency. This is one of the deepest lessons in science. Sometimes ideas outgrow the reasons they were created. A tool designed for one purpose becomes essential for another. A fix becomes a foundation. The cosmological constant is legendary not because Einstein was right or wrong, but because it shows how theory can carry hidden truths. It shows how equations can hold possibilities that take decades to reveal themselves. It also shows something deeply human. Einstein was not chasing mystery for its own sake. He was trying to make sense of the universe with the knowledge available to him. He trusted mathematics, but he also trusted the worldview of his time. By adding the cosmological constant, he delayed the acceptance of a dynamic universe. But he also preserved a doorway, a mathematical space where dark energy could later exist. Without that term, modern cosmology would look very different. Dark energy would feel like an alien addition. With it, dark energy feels like a natural extension of general relativity. This is why such a small term carries such a big legacy. It began as a quiet adjustment, a gentle push against gravity, a way to keep the universe still. It ended up becoming a key to understanding why the universe refuses to slow down. For years, Einstein's carefully balanced universe seemed safe. The equations were elegant, the assumptions felt reasonable. The universe, as far as anyone could tell, looked calm and unchanging. But while theory rested quietly on chalkboards, astronomers were beginning to notice something unsettling in the night sky, something that did not fit the idea of a still universe. It started as a whisper, not a shout. In the early decades of the 20th century, telescopes were improving. They could see farther and more clearly than ever before. Astronomers began studying faint, distant objects that looked like cloudy smudges of light. These were called nebulae. At the time, no one knew what they really were. Some believed they were gas clouds inside the Milky Way. Others suspected they might be something much larger. One astronomer in particular would change everything. His name was Edwin Hubble. Hubble worked at Mount Wilson Observatory in California, home to one of the most powerful telescopes of the era. Night after night, he observed these faint nebulae in detail. What he discovered was shocking. Many of these objects were not clouds inside our galaxy. They were entire galaxies of their own, vast systems of stars, millions or even billions of light years away. Suddenly the universe became much bigger, but Hubble did not stop there. He noticed something even more strange. When he analysed the light coming from these distant galaxies, it was shifted toward the red end of the spectrum. This effect became known as redshift. To understand redshift in simple terms, imagine hearing an ambulance siren as it moves away from you. The sound stretches and becomes lower in pitch. Light behaves in a similar way. When an object moves away from us, its light stretches, shifting toward red. When it moves toward us, the light compresses, shifting toward blue. Hubble found that almost every distant galaxy showed redshift, not just a little, a lot. This meant one thing: the galaxies were moving away from us. At first, this was confusing. Were we at the center of the universe, with everything else flying away? That idea felt uncomfortable and unlikely. But as more data came in, a clearer picture emerged. The farther away a galaxy was, the faster it appeared to be moving away. This relationship became known as Hubble's law. Distance and speed were linked. This was not random motion, it was systematic, organized, universal. The simplest explanation was also the most radical. Space itself was expanding. Galaxies were not racing through space like bullets. They were being carried apart as the space between them stretched. Just like dots on the surface of an inflating balloon, every galaxy saw every other galaxy moving away. There was no center, no edge, just expansion everywhere. This idea landed like an earthquake in science. The universe was not static, it was dynamic. It was changing. It had a past and a future. It might even have had a beginning. Overnight, Einstein's static universe was in trouble. If the universe was expanding, then the delicate balance created by the cosmological constant was unnecessary. Gravity alone could allow expansion. The idea of a perfectly still cosmos collapsed under the weight of observation. This moment marked a turning point in scientific history. For the first time, humanity had clear evidence that the universe evolves over time. Cosmology was no longer philosophy. It was observation-driven science. For Einstein, this discovery was deeply unsettling. Not because expansion was impossible within his theory, but because he had resisted it. His original equations, without the cosmological constant, naturally allowed expansion. The universe had been trying to tell him the truth all along. Legend has it that when Einstein learned of Hubble's discovery, he immediately recognized its importance. He accepted that the universe was expanding and reportedly abandoned the idea of a static cosmos. Whether or not every detail of that story is accurate, the impact is clear. The cosmological constant, once introduced to keep the universe still, now seemed like an unnecessary patch. Many physicists removed it entirely and moved forward with expanding universe models. For a while, it seemed like the story was settled. The universe was expanding. Gravity was slowing it down. The Big Bang theory began to take shape. Scientists imagined the universe starting hot and dense, then expanding and cooling over time. This picture made sense. It matched intuition. Expansion should gradually lose energy. Gravity should pull things together. The universe should slow down as it ages. Once again, comfort returned. But beneath the surface, a deeper question remained. How fast is the universe expanding? And is that expansion changing over time? At first, no one worried too much about this. Measuring cosmic expansion was difficult. The universe is vast, distances are enormous, data was limited. The assumption that expansion was slowing felt reasonable. After all, gravity had billions of years to do its work. Yet the universe was not finished challenging us. What made Hubble's discovery so powerful was not just that it proved expansion, it showed that space itself could change. This single realization shattered the idea of an eternal, unchanging cosmos. It introduced time into the structure of the universe. The universe now had a story. It was born, it evolved, and it would have a fate. This realization opened doors to entirely new questions. What started the expansion? How fast is it happening? What will happen in the far future? Einstein's equations were suddenly more relevant than ever. They were no longer theoretical exercises. They became tools for reading the universe's history. Ironically, the very equations Einstein once adjusted to avoid motion became the foundation for understanding cosmic motion. This is why the discovery of expansion changed everything overnight. It didn't just correct a small mistake, it rewrote humanity's place in the cosmos. We were no longer living in a timeless universe. We were living in a universe with a beginning. And yet, the most shocking part of this story had not arrived yet. Because even after accepting expansion, scientists believed the universe would eventually slow down. Gravity would take over, expansion would weaken, the cosmos would gently age. That assumption would hold for decades, until new observations revealed something even more disturbing. The universe was not slowing down, it was speeding up, and when scientists went searching for an explanation, they found themselves staring once again at a forgotten term in Einstein's equations. A term designed to keep the universe still, now reborn as the force pushing it apart. Few phrases in science are as famous as this one. My biggest blunder. It is often repeated in books, documentaries, classrooms, and videos as if it neatly summarizes one dramatic moment in scientific history. According to the popular story, Albert Einstein added the cosmological constant to his equations, later realized the universe was expanding, and immediately declared the constant his greatest mistake. End of story. But real science is rarely that clean, and real people are never that simple. When we look closely, the story of Einstein's so-called biggest blunder is not really about failure. It is about discomfort, caution, humility, and the way scientific ideas evolve over time. To understand it properly, we have to slow down and strip away the myth. First, did Einstein actually say those exact words? There is no written record of Einstein using the phrase biggest blunder in his published papers or personal writings. The quote is most commonly traced to conversations he had later in life, recalled by other physicists. The most famous source is George Gamow, a physicist who worked on cosmology and nuclear physics. Gamow reported that Einstein once referred to the cosmological constant as his biggest blunder. That does not mean the quote is fake, but it does mean it was informal, spoken in conversation, not a carefully considered public statement. Einstein was known for speaking candidly, sometimes playfully, especially later in life. He often exaggerated his own doubts and mistakes when talking to colleagues. This matters because the way the quote is used today suggests a clean reversal, as if Einstein confidently added the constant, then instantly regretted it once expansion was discovered. That is not what actually happened. Einstein did not wake up one morning and suddenly realize he was wrong. When Edwin Hubble's observations showed that the universe was expanding, Einstein accepted the result. He did not fight it. He did not deny it. He adjusted his view, as scientists are supposed to do. But this adjustment did not immediately turn the cosmological constant into a villain. At first, the constant simply became unnecessary. If the universe was expanding, then there was no need to artificially hold it still. Many physicists removed the term from their equations because it was no longer required. Not because it was mathematically wrong, but because it seemed physically unmotivated. In other words, the cosmological constant was not rejected as an error. It was set aside as an extra assumption that no longer seemed needed. Einstein's regret, if we want to call it that, was subtle. It was not about bad mathematics. It was about missed courage. Einstein later acknowledged that his original equations, without the cosmological constant, naturally predicted expansion. He had briefly glimpsed that possibility and then turned away from it. In hindsight, he recognized that he could have predicted an expanding universe before anyone observed it. That realization likely stung. But notice what this regret is really about. It is not about adding the constant. It is about doubting the implication of his own theory. It is about not trusting the mathematics far enough. This is very different from the simplified myth. Popular retellings often frame Einstein as someone who forced the universe to match his beliefs, then paid the price. That story is appealing because it feels moral. Pride leads to error. Observation corrects arrogance. Lesson learned. But the truth is more human and more interesting. Einstein was not arrogant. He was cautious. He was operating in a scientific culture where bold theoretical claims without observational support were risky. Cosmology was young. Telescopes were limited. The idea of a dynamic universe had no empirical foundation at the time. Choosing stability was not an act of ego, it was an act of restraint. This is why scientists oversimplified the moment later. Stories are easier to tell when they have clear heroes and clear mistakes. A genius makes a blunder. The universe proves him wrong. End of drama. But real science unfolds slowly. Ideas are tested, revised, abandoned, revived. The cosmological constant itself is proof of that. It went from useful to unnecessary to embarrassing to essential. If Einstein truly believed it was his greatest mistake, the irony is almost poetic. That mistake turned out to describe something real, something dominant, something fundamental. This forces us to rethink what scientific mistakes even are. Was the cosmological constant a mistake if it later helped explain accelerating expansion? Or was it an idea introduced for the wrong reason, but pointing in the right direction? Science is full of examples like this. Concepts created to solve one problem end up solving another. Assumptions made cautiously turn out to be profound. Temporary fixes become permanent features. In this light, Einstein's blunder looks less like failure and more like incomplete insight. It also highlights Einstein's humility. Despite his reputation as an untouchable genius, Einstein was deeply aware of his limitations. He openly admitted uncertainty. He changed his views when evidence demanded it. He did not cling to ideas out of pride. This humility is often lost in popular portrayals. Einstein is shown as either infallible or foolish, depending on the story being told. The reality is more inspiring. He was a thinker willing to say, "I was uncomfortable with this idea, and later I learned I could have been braver." That is not weakness. That is intellectual honesty. It is also worth noting that Einstein never fully embraced the modern concept of dark energy. He did not live to see the discovery of accelerating expansion. He never reinterpreted the cosmological constants in that context. Any claim that he knew all along is just as misleading as the claim that he completely rejected the idea. Einstein existed in the middle, a space where uncertainty lives. This is why the biggest blunder story should not be used as a punchline. It should be used as a lesson. A reminder that science is not about dramatic reversals. It is about careful steps, hesitant conclusions, and constant revision. Oversimplifying this moment does a disservice not just to Einstein, but to science itself. It suggests that progress happens through sudden embarrassment rather than long-term curiosity. It turns humility into shame. In reality, humility is one of science's greatest strengths. Einstein's willingness to accept expansion when evidence appeared is exactly what made his work endure. His readiness to acknowledge discomfort, to revisit assumptions, to let the universe surprise him, is what kept his theories alive. The cosmological constant is not a scar on Einstein's legacy. It is a mirror. It reflects how even the greatest minds wrestle with uncertainty. And perhaps the most important point is this: Einstein's story reminds us that understanding often arrives in layers. An idea can be incomplete and still meaningful, wrong in motivation, yet right in consequence. If Einstein had never added the cosmological constant, modern cosmology would have had to invent something very similar to explain dark energy. The universe did not change, our interpretation did. So was the cosmological constant Einstein's biggest regret? Maybe, but was it also one of his deepest insights? That question is harder to dismiss. Because sometimes the ideas we least trust end up telling the truest stories. And sometimes the universe rewards humility, not by avoiding mistakes, but by turning them into revelations. In the next part of our journey, we will move beyond Einstein and into a new cosmic puzzle. Expansion alone was not the end of the story. It created new expectations. Expectations the universe would soon violate once again, and once more, reality would refuse to stay comfortable. For a while, it seemed like science had finally found solid ground. The universe was expanding. That strange and unsettling idea had been absorbed, tested, and accepted. Telescopes confirmed it again and again. Galaxies were moving away from each other. Space itself was stretching. The universe had a history. It was no longer eternal and still. But acceptance did not mean understanding was complete. Expansion alone raised a new question, one that felt simple at first but quickly turned into a deep cosmic puzzle. If the universe is expanding, what is happening to that expansion over time? Is it slowing down, staying steady, or changing in some unexpected way? At first, scientists thought they already knew the answer. Gravity exists everywhere. Every galaxy pulls on every other galaxy. Every cluster of matter creates attraction. Gravity is patient and relentless. It may be weak over large distances, But given enough time, it always adds up. So the expectation was clear and logical. If the universe began expanding long ago, gravity should be working against that expansion. Over billions of years, expansion should gradually slow down. The universe should be coasting, losing speed, like a ball thrown upward against gravity. This idea felt almost obvious. It matched everyday experience. It matched intuition. It matched everything scientists understood about gravity. In this picture, the universe expands quickly at first, then more slowly as time passes. Depending on how much matter exists, expansion might eventually stop. The universe could collapse back inward, or it could expand forever at a slower and slower rate. Either way, one thing seemed certain: expansion should decelerate. This assumption became the foundation of modern cosmology for decades. Scientists built models around it. They debated how much matter existed and what the final fate of the universe would be. Would it collapse? Would it expand forever? Would it balance on a knife edge? These were big questions, but they all shared a quiet agreement. Gravity was in charge. Then observations began to whisper something strange. As telescopes improved and astronomers started measuring distant objects more carefully, cracks appeared in the comfortable picture. At first, the data was confusing. Distances in the universe are hard to measure. Cosmic scales are enormous. Errors are common. No one rushed to conclusions, but as measurements improved, the whispers grew louder. The universe did not seem to be slowing down, as expected. This was deeply unsettling, not because the data was wrong, but because the implication was hard to accept. If expansion was not slowing, then gravity was not winning. Something else was at play. Scientists double-checked everything. Instruments, calculations, assumptions. They questioned their methods again and again. This was not the kind of result you announce lightly. It challenged decades of thinking. The disturbing possibility began to emerge. What if the universe is not just expanding, but accelerating? At first, this idea sounded almost absurd. Acceleration means gaining speed. It means something is pushing. But what could possibly push the entire universe outward? There was no obvious candidate. No known force behaves this way on cosmic scales. Gravity only pulls. Electromagnetism cancels out over large distances. Nuclear forces are confined to tiny scales. There was nothing left. And yet, the delta refused to go away. The more scientists looked, the more consistent the picture became. Distant objects appeared farther away than they should be if expansion were slowing. The universe, it seemed, had picked up speed. This was not a small adjustment. It was a complete reversal of expectation. For decades, scientists had assumed gravity would act like a brake. Now it looked like there was an accelerator. The universe was not just moving outward, it was being pushed outward faster and faster as time passed. This realization marked the birth of a new cosmic problem. Expansion alone was not enough to explain reality. Something was missing, and this missing piece was not small. It dominated the behavior of the universe on the largest scales. What made this especially troubling was how late this effect appeared. Early in the universe's history, matter and radiation dominated. Gravity should have been strongest then. Expansion should have slowed the most. Instead, acceleration seemed to take over much later, when the universe was already old and spread out. This timing felt unnatural. Why would a mysterious push wait billions of years to become important? Why would it only dominate when space itself became large? These questions had no easy answers. Some scientists wondered if gravity itself behaved differently on large scales. Maybe general relativity breaks down across billions of light years. Maybe something subtle changes when space-time stretches too much. Others considered the possibility that empty space itself has properties we do not understand. That space is not passive, that it can act, influence, and even dominate. This idea felt uncomfortable, but familiar. It echoed a forgotten concept from earlier in the century. A small term once added to equations to keep the universe still. A term that behaved like a push built into space itself. At this stage, scientists were not ready to embrace that idea fully. They explored every alternative first: modified gravity, exotic matter, measurement errors, anything that could avoid invoking a mysterious new component of the universe. But the observations became too strong to ignore. The universe was not slowing down, it was speeding up. This realization changed the tone of cosmology. The field moved from confidence back to uncertainty. Models that once felt complete now felt fragile. The universe had revealed yet another layer of complexity. What made this moment so powerful was how unexpected it was. Expansion itself had already been a shock. Acceleration felt like the universe was actively defying logic. It was no longer enough to say, "The universe is expanding." That statement had become incomplete. Misleading even. A better statement was this: the universe is expanding, and something is driving that expansion faster over time. That something had no name yet, no clear identity, no physical explanation, but its fingerprints were everywhere. It shaped the distances between galaxies. It influenced the future of cosmic structure. It determined whether the universe would thin into darkness or tear itself apart. This new problem forced scientists to confront a humbling truth. We did not understand the majority of what exists. Matter, stars, planets, gas, dust, and everything familiar made up only a small fraction of the universe's behavior. The dominant influence was invisible. This was not a failure of science. It was science working as it should. Observation challenged theory. Theory adjusted. New questions emerged. And once again, Einstein's work waited quietly in the background. His equations did not forbid acceleration. They did not reject a push from space itself. In fact, they allowed it. The question was no longer whether the universe expands. The question became why expansion accelerates. Answering that question would require a new idea, an idea so strange that it would reshape our understanding of reality once more. In the late 1990s, something extraordinary happened in astronomy. Not a dramatic explosion in space, not a new telescope image that went viral, but something quieter and far more unsettling. A careful measurement, a comparison of light, a conclusion that nobody was expecting. This was the moment when the universe revealed its most disturbing secret so far. The universe was not just expanding, it was accelerating. To understand why this discovery was so shocking, we need to understand what scientists were actually trying to measure at the time. Astronomers were not hunting for dark energy. They were not trying to prove Einstein wrong or right. They were asking a much simpler question. How fast is the universe slowing down? Remember, by the 1990s, the expanding universe was accepted. The Big Bang model was well established. What remained uncertain was how gravity was affecting expansion over time. Was the universe slowing a little? A lot? Would it eventually stop and collapse or expand forever? To answer this, astronomers needed a way to measure cosmic distances very precisely. And for that, they turned to one of the most powerful tools in observational astronomy: supernovae. Not all supernovae are the same, but one type is especially useful. Type Ia supernovae. These explosions occur when a specific kind of star reaches a precise limit and detonates in a predictable way. Because of this, they shine with almost the same true brightness every time. This makes them cosmic measuring tools. If you know how bright something truly is and you see how dim it appears from Earth, you can calculate how far away it is. Astronomers call these objects standard candles. In simple terms, type Ia supernovae allow scientists to measure distances across billions of light years. Two independent teams began using these stellar explosions to map the expansion of the universe. One was the Supernova Cosmology project, the other was the High Z Supernova Search team. They worked separately. They used different telescopes, different methods, different analysis techniques. This independence is crucial because it removes bias. If both teams reach the same conclusion, the results would be difficult to dismiss. Their plan was straightforward. Observe distant supernovae, measure their brightness. Compare how far away they are to how fast they appear to be moving away due to cosmic expansion. From this, infer whether expansion is slowing down. That was the expectation. What they found instead was deeply confusing. The distant supernovae were dimmer than expected, not just a little, enough to matter. At first, this raised alarms. Maybe dust was blocking the light. Maybe the supernovae were different in the past. Maybe the instruments were miscalibrated. Every possible explanation was considered. Months turned into years of checking, rechecking, and arguing. Scientists are trained to distrust surprising results, especially ones that challenge fundamental assumptions. But the data refused to go away. When the teams accounted for every known effect, one conclusion remained. The supernovae were farther away than they should be if expansion were slowing. The only explanation was breathtaking. The universe had expanded less in the past than expected, which means it is expanding faster now. In other words, expansion is accelerating. This result landed like a shockwave. Acceleration means energy. It means a push. It means something is actively driving the universe apart. But nothing in standard cosmology predicted this. Gravity should slow expansion. Matter should pull inward. There was no known force capable of doing the opposite on cosmic scales. Yet the evidence was clear. Two independent teams. Same conclusion. In 1998, both groups announced their results. The universe is not slowing down. It is speeding up. This was one of the most shocking discoveries in modern science. It overturned decades of expectation overnight. Textbooks became outdated. Models had to be rewritten. The future of the universe suddenly looked very different. Scientists were stunned not just by the result, but by its implications. If expansion is accelerating, then something invisible and powerful dominates the universe, something that does not behave like matter or radiation. This mysterious component was given a simple name: dark energy. The name was not meant to explain. It was meant to label ignorance. Dark because we cannot see it. Energy because it does something. It drives acceleration. At this point, the scientific community faced a choice. Either the laws of gravity are wrong on large scales, or the universe contains a new form of energy we do not understand. Neither option was comfortable. As scientists searched for explanations, they turned back to the foundations of cosmology, back to general relativity, back to Einstein's equations. And there it was, a forgotten term, quietly waiting, the cosmological constant. The same term Einstein once added to keep the universe still. The same term later discarded as unnecessary. Now it returned with new meaning. The cosmological constant behaves exactly like dark energy. It represents a constant energy density of empty space. It creates a steady outward push. It does not dilute as the universe expands. In fact, as space grows, its total effect grows stronger. This was almost unbelievable. Einstein had introduced the mathematics for dark energy decades before its discovery. Not intentionally, not knowingly, but unmistakably. The realization sent a chill through cosmology. A term once considered a mistake now looked essential. A patch became a pillar. This did not mean the mystery was solved. Far from it. Even if dark energy behaves like the cosmological constant, we still do not know what it actually is. Why does empty space have energy? Why is its value so small yet so dominant? Why did it begin to dominate only recently in cosmic history? These questions remain unanswered, but the discovery of accelerating expansion forced scientists to accept one thing. The universe is stranger than imagined, stranger even than Einstein expected. This moment also changed how scientists view theory and observation. For decades, theory suggested gravity would slow expansion. Observation said otherwise, and observation won. This is not a failure of theory. It is how science grows. Theories are refined, assumptions are questioned. Reality always gets the final word. The shock of the accelerating expansion rippled far beyond cosmology. It influenced particle physics, quantum theory, and philosophy. It raised questions about the nature of nothingness, about whether empty space is truly empty, about whether our understanding of reality is fundamentally incomplete. It also transformed Einstein's legacy yet again. Once he was the man who resisted expansion. Then he became the man whose equations allowed it. Now he appeared as the man who unknowingly laid the groundwork for the universe's greatest mystery. The discovery of dark energy was not just a new chapter, it was a turning point. From that moment on, cosmology entered a new era, an era defined not by what we know, but by what we do not. And at the center of that ignorance lies a quiet question, echoing through time. Did Einstein accidentally predict dark energy? By the time scientists accepted that the universe is accelerating, a new word entered public conversation almost overnight: dark energy. It sounded dramatic, mysterious, and slightly frightening. And in many ways, it is all of those things. But it is also one of the most misunderstood ideas in modern science. To understand dark energy clearly, we must begin by saying what it is not. Dark energy is not a hidden substance, floating through space like invisible gas. It is not clouds of unknown particles pushing galaxies apart. It is not a force shooting outward from the center of the universe. And it is definitely not science fiction energy waiting to be harvested. Most importantly, dark energy is not dark matter. This confusion is extremely common, and it creates endless misunderstanding. Dark matter and dark energy share only one thing: the word dark. They are dark because we cannot see them directly. Beyond that, they are completely different ideas that solve completely different problems. Dark matter behaves like matter. It clumps, it gathers around galaxies, it pulls things inward through gravity. Without dark matter, galaxies would not hold together. Stars would fly apart. Dark matter acts like invisible glue. Dark energy does the opposite. Dark energy does not clump. It does not gather around galaxies. It does not pull anything inward. It spreads smoothly through all of space, and instead of pulling, it pushes. If dark matter is cosmic glue, dark energy is cosmic pressure. This pressure does not come from explosions or motion, it comes from space itself. This is the hardest idea to accept, because we are used to thinking of space as empty, nothingness, a vacuum where nothing happens. But modern physics tells us that empty space is not truly empty. Even in regions where there are no stars, no gas, no dust, and no particles, space still exists. And according to our best theories, that space has properties. Think of space not as a void, but as a stretched fabric. When more space exists, more of that fabric exists. And if that fabric carries energy, then creating more space creates more energy. This where dark energy behaves in a very strange but consistent way. As the universe expands, matter spreads out. Radiation weakens. Gravity's influence fades across large distances. But dark energy does not thin out. Its energy density stays roughly constant everywhere. That means as space expands, the total amount of dark energy increases. More space means more dark energy. More dark energy means stronger outward push. Stronger push causes faster expansion. Faster expansion creates more space. This feedback loop is why the universe accelerates. This behavior is very different from anything we experience in daily life. Most energies weaken as they spread out. Dark energy does not. This is why scientists often describe dark energy as a kind of negative pressure. Pressure usually pushes inward or outward depending on conditions. In this case, the pressure is built into space itself, and pushes outward uniformly. No center, no direction, just expansion everywhere. This idea fits perfectly into the framework created by Albert Einstein. His theory of general relativity allows space itself to carry energy. It allows empty space to influence the shape and motion of the universe. This is exactly what the cosmological constant represents. The cosmological constant is not a force. It is not a particle. It is a number that describes how much energy empty space has. That energy acts like a constant pressure, pushing space-time apart. In simple terms, the cosmological constant and dark energy behave the same way. They both fill space evenly. They both cause acceleration. They both remain constant as the universe expands. This is why many scientists believe dark energy is simply the cosmological constant. But believing this does not mean we understand it. Here is the uncomfortable truth. When physicists try to calculate the energy of empty space using quantum theory, they get a number that is wildly wrong. Not a little wrong, not 10 times wrong, off by an amount so huge it is almost embarrassing. The theoretical prediction is about 120 orders of magnitude larger than what we observe. That mismatch is one of the biggest unsolved problems in physics. So even if dark energy behaves like the cosmological constant, we do not know why its value is what it is. This is why scientists are careful. Dark energy might be vacuum energy, or it might be something slightly different that just looks similar. It might change slowly over time, or it might be truly constant forever. Right now, observations suggest it behaves very much like Einstein's cosmological constant. But science remains cautious. The key takeaway is this: dark energy is not a thing moving through space. It is a property of space. It does not pull. It pushes. It does not gather. It spreads. It does not weaken. It dominates. This also explains why dark energy only becomes important on the largest scales. Inside galaxies, gravity overwhelms it. Inside solar systems, it is completely irrelevant. You do not feel dark energy pulling you apart. Earth is safe. Atoms are safe. Dark energy only reveals itself across billions of light years. This scale dependence is why it escaped detection for so long. We had to look deep into the universe's past to see its effects. Nearby galaxies are too close together for dark energy to matter much. Distant galaxies show the difference clearly. Once scientists understood this, confusion began to clear. Dark energy is not magic. It is not an add-on. It fits naturally into the equations that describe space-time. The confusion comes from our intuition. We are not built to imagine space having energy. We are not built to imagine nothing doing something. But the universe does not care what feels intuitive. When Einstein added the cosmological constant, he was unknowingly allowing for exactly this possibility. He did not call it dark energy. He did not imagine accelerating expansion, but the mathematics was already there. This is why the connection feels almost eerie. A term created to stop motion now explains runaway motion. A fix designed for stillness now drives change. This does not mean Einstein secretly knew the truth. It means he built a theory flexible enough to contain it. And this flexibility is what makes general relativity so powerful. It does not dictate what fills the universe. It describes how the universe responds to whatever fills it. Dark energy fits into that response perfectly. Still, many questions remain open. Is dark energy truly constant? Will it remain the same forever? Or will it change, weaken, or grow stronger over time? Could it eventually tear the universe apart? Or fade away? These questions define modern cosmology. But at its core, dark energy is simpler than it sounds. It is not a mysterious substance racing through space. It is the quiet energy of space itself, revealed only when the universe becomes large enough to notice. And that realization changes how we think about emptiness. Empty space is not nothing. Nothingness has structure, and that structure shapes the fate of everything. At this point in the story, we arrive at the question that has been quietly growing in the background from the very beginning. It is the question that gives this entire journey its meaning. Was Albert Einstein accidentally right after all? Not right in the way textbooks usually mean. Not right because he confidently predicted dark energy and waited for the universe to confirm it. But right in a stranger, more unsettling way. Right because the mathematics he wrote down, for reasons he did not fully trust, turned out to describe reality decades later. To answer this honestly, we have to compare two things carefully: the cosmological constant and dark energy. On the surface, they look almost identical. Both represent an energy associated with empty space. Both are spread uniformly throughout the universe. Both create a repulsive effect that causes expansion to accelerate. Both remain constant as the universe grows. From the point of view of Einstein's equations, dark energy behaves exactly like the cosmological constant. This is why many cosmologists today use the two terms almost interchangeably. When they model the universe, they often assume dark energy is simply the cosmological constant. Not because it is proven beyond doubt, but because it fits the data remarkably well. That alone is astonishing. A term introduced in 1917 to keep the universe static turns out to explain observations made in the 1990s. The math did not need to be rewritten. It just needed to be reinterpreted. This leads to a tempting conclusion. Einstein predicted dark energy, but that conclusion needs to be handled with care. Einstein did not predict dark energy in the usual sense of the word. He did not propose a mysterious energy that would one day accelerate the universe. He did not anticipate supernova measurements or cosmic acceleration. His intention was almost the opposite. He wanted to prevent change, not explain runaway expansion. So in what sense could he be considered right? The answer lies in the nature of scientific prediction. In popular imagination, prediction is intentional. A scientist proposes an idea, makes a clear forecast and waits for confirmation. But in real physics, prediction often works differently. Sometimes equations reveal possibilities before anyone understands their meaning. This happens more often than we like to admit. General relativity predicted black holes before physicists believed they could exist. It predicted gravitational waves long before technology could detect them. It allowed for expanding universes before astronomers observed them. In each case, the mathematics came first. Interpretation followed later. The cosmological constant belongs to this pattern. Einstein introduced it as a mathematical possibility allowed by his theory. He did not invent it arbitrarily. His equations permitted it naturally. He simply chose to include it. What he did not foresee was how that term would behave in a dynamic universe. Once expansion was accepted, the cosmological constant transformed from a stabilizing trick into a driver of acceleration. The same term under different conditions revealed a completely different role. This is where the idea of prediction, without intention, becomes important. Einstein did not predict dark energy in the sense of making a claim about the future universe, but his theory predicted the possibility of dark energy existing. It created space, both mathematically and conceptually, for such an energy to exist. In that sense, yes, Einstein was accidentally right. This kind of accidental truth is not rare in physics. It is almost a defining feature of deep theories. The more fundamental a theory is, the more it contains beyond its creator's imagination. Quantum mechanics is filled with examples like this. Equations written to describe atoms later explained semiconductors, lasers, and modern computing. Maxwell's equations predicted radio waves before anyone knew they existed. Dirac's equations predicted antimatter before it was observed. None of these discoveries came from intentional foresight. They came from trusting mathematics. This raises a deeper question. Can science discover truth by accident? The uncomfortable answer is yes. And it happens all the time. Scientists often aim to solve one problem and end up uncovering something far bigger. The universe does not reveal itself in tidy steps. It reveals itself through patterns, structures, and equations that carry more information than we initially extract from them. In this light, Einstein's cosmological constant looks less like a mistake and more like an unopened letter. The message was there. We just did not know how to read it yet. But there is another layer to this story that makes it even more interesting. Even today, we do not know whether dark energy truly is the cosmological constant. Observations tell us that dark energy behaves very much like it, but small differences could exist. Dark energy might change slowly over time. It might not be perfectly constant. It might come from fields we have not yet discovered. So while the match is impressive, it is not guaranteed to be exact. This uncertainty matters because it keeps the question open. If dark energy turns out to be something dynamic, something slightly different from a constant vacuum energy, then Einstein's role becomes more indirect. He would not have predicted dark energy itself, but rather created the framework in which it could be understood. And that distinction matters. Einstein's greatest contribution may not be any single term or equation. It may be the way he taught us to think about space and time. By turning space into a physical entity with properties, he made it possible to imagine empty space doing something. Before Einstein, the idea that nothing could influence everything would have sounded absurd. After Einstein, it became mathematically natural. This is why the math fits so well. Not because Einstein guessed correctly, but because he asked the right kind of questions. He asked what space is. He asked how gravity really works. He asked whether geometry itself could be physical. Dark energy lives inside those questions. So was Einstein accidentally right? Yes, in the sense that his equations contained the seed of the answer. No, in the sense that he did not foresee the full implications. And maybe that is the most honest outcome. Science does not progress through perfect foresight. It progresses through frameworks that are flexible enough to absorb surprise. Einstein's work did not tell us what dark energy is, but it told us where to look. It told us how to describe it once we found it. It told us that space itself could matter. That is a different kind of correctness, a deeper one. It also forces us to rethink how we judge scientific success. Was Einstein wrong because he resisted expansion? Or was he right because his theory survived every test thrown at it, even ones he never imagined? The story of dark energy suggests that being right in science does not mean predicting every detail. It means building something that reality can live inside. General relativity has done that for over a century. And the cosmological constant, once seen as an embarrassment, now sits at the heart of our best model of the universe. That alone should make us cautious about labeling ideas as mistakes too quickly. In physics, yesterday's error can become tomorrow's insight. This is why the question, was Einstein accidentally right, does not have a simple yes or no answer. It has a richer answer, one that reflects how science actually works. Einstein was not a prophet, he was a builder. He built a structure strong enough to hold truths he never fully explored. And dark energy is one of those truths. By now, dark energy no longer sounds like a strange add-on to cosmology. It feels central. It shapes the expansion of the universe. It dominates its future. It fits naturally into Einstein's equations. And yet, at the deepest level, dark energy creates what many physicists consider the biggest problem in all of modern physics. Not the hardest problem, the biggest. The reason is simple to state, but deeply unsettling to understand. When physicists try to calculate the energy of empty space using our best theories, they get an answer that is catastrophically wrong. To see why this is so serious, we need to talk about how physicists think about empty space. In quantum physics, empty space is not truly empty. Even in a perfect vacuum, fields still exist. These fields fluctuate. Particles briefly appear and disappear. Energy is constantly bubbling in and out of existence. This is not speculation. These effects are measured and confirmed in laboratories. According to quantum field theory, every point in space contains this restless activity. All of it contributes to the energy of the vacuum. So physicists did what physicists always do. They tried to calculate how much energy empty space should have. The result was shocking. The predicted energy of the vacuum was not just a little larger than what we observe as dark energy. It was larger by a factor so enormous that it almost defies language. Depending on how the calculation is done, the mismatch is about 1, followed by 120 zeros. That is not a typo. If dark energy were as strong as quantum theory predicts, the universe would have blown itself apart instantly after the Big Bang. Galaxies would never have formed. Stars would never have existed. Life would be impossible. But the universe exists. Galaxies exist. We exist. So something is deeply wrong. Either our understanding of quantum physics is incomplete, or our understanding of gravity is incomplete, or both. And since these two theories form the foundation of modern physics, this gap strikes at the heart of everything we think we know. This mismatch is known as the cosmological constant problem, and it is widely regarded as the worst prediction in the history of science. Not because the math is sloppy, but because the math is precise and still wrong. What makes this problem especially disturbing is that it is not subtle. It is not hidden behind experimental uncertainty. It is not waiting for better instruments. It is screaming at us. The universe is telling us that our theories, as powerful as they are, do not fully understand empty space. This raises a difficult question. If the cosmological constant fits observation so well, why does theory fail so badly? One possibility is that quantum vacuum energy somehow cancels itself out almost perfectly, leaving behind a tiny leftover that we observe as dark energy. But no known mechanism explains such precise cancellation. It would require an almost miraculous balance. Another possibility is that dark energy is not vacuum energy at all, but something else that just behaves similarly. A new field, a slow-changing energy, a property of space-time we have not yet identified. Or perhaps gravity itself behaves differently when space becomes extremely large. Maybe Einstein's equations are not the final word on cosmic scales. Each of these possibilities is unsettling, because each implies that our current picture of reality is incomplete. This is why dark energy is not just another mystery, it is a stress test for physics. It sits at the intersection of two great theories: quantum mechanics, which describes the smallest scales with incredible accuracy, and general relativity, which describes the largest scales with equal success. Individually, these theories work beautifully. Together, they clash. Dark energy lives exactly where they meet. This is why Einstein's equations are still central to the problem. Even though they are over a century old, they remain the best description of gravity we have. Every observation of cosmic expansion, gravitational lensing, black holes and gravitational waves confirms their accuracy. Dark energy does not break Einstein's theory. It fits inside it. The problem is not that general relativity cannot describe dark energy. The problem is that when we try to explain dark energy using quantum physics, the numbers explode. This suggests that something fundamental is missing. It could mean that empty space behaves differently than quantum theory predicts when gravity is included. Or it could mean that gravity emerges from deeper principles we do not yet understand. Either way, the universe is telling us that our understanding of reality has cracks. This is not a sign of failure. It is a sign of progress. Throughout history, the biggest breakthroughs in physics have come from precisely these kinds of contradictions. When equations work too well in one domain and fail spectacularly in another, it usually means we are standing at the edge of a deeper theory. Newton's gravity failed at high speeds and strong fields, leading to relativity, Classical physics failed at small scales, leading to quantum mechanics. Now both theories strain when faced with dark energy. The stakes could not be higher. Dark energy determines the fate of the universe. If it remains constant, the universe will expand forever, growing colder and emptier. If it changes, the future could be very different. Structures could tear apart, or expansion could slow and reverse. But beyond fate, dark energy challenges our understanding of existence itself. It asks whether nothingness can have energy, whether space is a substance, whether reality is built from geometry, fields, or something even deeper. It also humbles us. Despite all our technology, all our equations, all our observations, we do not understand the dominant component of the universe. Everything we see, from stars to galaxies to planets, is a minority player. The main actor remains invisible. This realization forces a shift in perspective. Physics is not close to being finished. We are not polishing details. We are missing something fundamental. And yet, we are not lost. Einstein's equations still guide us. They give us a framework that works astonishingly well. They tell us how space responds to energy, even when we do not fully understand that energy. Dark energy has not destroyed general relativity. It has highlighted its power and its limits at the same time. That combination is rare. The universe is not mocking us. It is inviting us to go deeper. The cosmological constant problem is not just a technical issue for specialists. It is a signpost. It tells us that the story of space, time, and energy is not complete. That reality still holds secrets large enough to reshape physics. And perhaps most importantly, it reminds us of something Einstein himself understood very well: that the universe is under no obligation to make sense to us easily. By the time scientists accepted dark energy as real, one thing became painfully clear. Even though Einstein's equations could describe it, they did not explain it. The cosmological constant fit the observations, but it felt unsatisfying. Too quiet, too mysterious, too disconnected from the rest of physics. So naturally, scientists began to ask a new question. What if dark energy is not just a constant number written into the fabric of space? What if it is something deeper, something dynamic, something that changes over time? This question marks the beginning of modern cosmology's most active and creative phase, a phase where Einstein's ideas are not discarded but challenged, stretched, and tested from every angle. The first set of alternatives focuses on changing dark energy itself. Instead of treating dark energy as a constant property of empty space, some theories imagine it as a field, similar in spirit to fields we already know, like electromagnetic fields. This idea suggests that dark energy might evolve slowly as the universe ages. In these models, dark energy was weaker in the past and became stronger only recently. This could explain why cosmic acceleration appeared late in the universe's history. It would no longer feel like a coincidence. It would be part of a gradual process. These ideas are often grouped under the label dynamic dark energy. One popular example imagines a field that rolls slowly over time, changing its influence on expansion. Not suddenly, not violently, just enough to matter over billions of years. What makes these ideas attractive is that they offer flexibility. If dark energy can change, then future observations might reveal subtle differences from a pure cosmological constant. Scientists could test these models by measuring expansion more precisely across cosmic time. But there is a problem. So far, observations show that dark energy behaves remarkably like a constant. Not perfectly proven, but close enough that dynamic models struggle to show clear advantages. Every time data improves, the cosmological constant continues to fit just as well. This does not kill dynamic dark energy theories, but it keeps them on a tight leash. Another approach takes a more radical step. Instead of changing dark energy, it changes gravity. These theories ask a bold question. What if the universe is not accelerating because of a mysterious energy, but because gravity itself behaves differently on large scales. After all, Einstein developed general relativity based on what was observable in his time, mostly stars, planets, and light within galaxies. Perhaps gravity works one way locally, but another way across billions of light years. Modified gravity theories attempt to tweak Einstein's equations so that acceleration emerges naturally, without dark energy. Some of these theories add extra dimensions. Others introduce new gravitational fields. Some alter how space-time responds to matter when densities become extremely low. On paper, these ideas are elegant. They try to explain acceleration without invoking an unknown energy filling space. But once again, reality pushes back. Einstein's theory has passed every test thrown at it so far, from the orbit of Mercury to gravitational waves to black hole images. Any modification must match all of those successes, while also explaining cosmic acceleration. That is an extremely high bar. Many modified gravity theories can explain acceleration, but they struggle elsewhere. They predict effects that are not observed, or they break down in strong gravitational fields, or they introduce new problems that are just as mysterious as dark energy. This is why none of them has replaced Einstein's theory. Then there are even more speculative ideas. Some physicists explore whether dark energy could be an illusion caused by how we average the universe's structure. Galaxies are not evenly distributed. Matter clumps, voids grow. Perhaps this uneven structure affects expansion in subtle ways. Others wonder whether our universe is just one of many, and dark energy reflects conditions unique to ours. In such scenarios, the value of dark energy is not explained by deep laws, but by cosmic chance. These ideas are controversial, difficult to test, and often philosophical, but they reflect something important. Scientists are not standing still. They're exploring every possible path. Despite all this creativity, one fact remains stubborn. None of these alternatives has clearly beaten the cosmological constant. Einstein's equations, with that small added term, still describe the universe better than anything else we have. They are simple, predictive, consistent with observation. This does not mean they are final. It means they are strong. Science rarely moves by replacing great theories overnight. Instead, it stretches them to their limits, looking for cracks. So far, Einstein's framework bends, but it does not break. This is why modern cosmology feels unfinished rather than broken. Dark energy has not overturned physics. It has exposed its boundaries. Every new telescope, every new survey, every new measurement tightens the constraints. Scientists are watching closely for any sign that dark energy changes over time. Any deviation from a constant behavior would point toward new physics. So far, the universe remains frustratingly consistent. This consistency is both comforting and unsettling. Comforting because it suggests we are not wildly wrong. Unsettling because it means the simplest explanation might be correct, even if we do not understand it. The cosmological constant may be the answer, not because it is elegant, but because the universe seems to insist on it. This brings us to an important realization. Science is not a straight line from ignorance to truth. It is a conversation, a back and forth between imagination and observation. Einstein began that conversation by redefining space and time. Others extended it by discovering expansion. Later generations uncovered acceleration. Now we stand at a point where the questions are deeper than ever. What is empty space? Why does it have energy? Why does that energy dominate now? We do not yet know, and that is exactly how science is supposed to feel at the frontier. The competing theories beyond Einstein are not signs of confusion. They are signs of vitality. They show that cosmology is alive, questioning itself, refusing to settle too quickly. Einstein's work still anchors this exploration, not as a final answer, but as a foundation, a language we continue to use, even as we search for something deeper. This is what an unfinished story looks like. Not chaos, not failure, but motion. The universe keeps expanding. Our ideas keep evolving. When we talk about dark energy, it can feel abstract, invisible energy, empty space, equations and observations spread across billions of light years. But behind all of that complexity lies a very simple and very human question. What will happen to the universe? Not tomorrow, not in 1,000,000 years, but in the deepest future imaginable. Dark energy is not just a curiosity for scientists. It is the deciding factor in the universe's destiny. Whatever dark energy truly is, it controls how the story of the cosmos ends. To see why, we need to think about the universe as a system that evolves over time. From the moment of the Big Bang, the universe has been changing. It expanded rapidly, cooled down, formed particles, atoms, stars, galaxies, and planets. Every chapter of cosmic history depended on how fast space expanded and how strongly gravity pulled things together. For a long time, scientists believed gravity would eventually decide the ending. Gravity pulls matter inward. Given enough time, it could slow expansion, stop it, and possibly reverse it. This idea led to visions of a collapsing universe where everything falls back together in a fiery finale. That possibility is now almost certainly off the table. Dark energy changed the rules. Because dark energy drives acceleration, it works directly against gravity on the largest scales. And the more the universe expands, the more dominant dark energy becomes. This gives it enormous power over the long-term future. Right now, dark energy already outweighs matter and radiation combined. As time goes on, that dominance only increases. This leads us to the most likely future scenario: endless expansion. In an expanding universe dominated by dark energy, galaxies continue to move farther apart. Over billions of years, distances become so vast that galaxies outside our local group disappear from view. Their light stretches, weakens, and eventually fades beyond detectability. This does not happen suddenly. It happens quietly. Stars continue to form for a long time, but eventually the raw material for new stars runs out. Existing stars burn through their fuel and fade. Galaxies grow dimmer. The universe becomes darker. This slow fading leads to what scientists call heat death. The phrase sounds dramatic, but the idea is simple. Heat death does not mean everything becomes hot. It means everything reaches the same temperature. No energy differences remain. No gradients exist to power change. In such a universe, there is no free energy left to do work. No new stars can form. No complex structures can arise. Time continues, but nothing meaningful happens. Dark energy plays a key role in this outcome. By accelerating expansion, it spreads matter thinner and thinner. It isolates regions of space. It prevents gravity from gathering material into new structures. Even galaxies themselves are affected. Within galaxies, gravity still holds stars together. Dark energy is too weak on small scales to tear galaxies apart. But over extremely long times, as galaxies drift away from one another, interactions become rare. Mergers stop. Cosmic evolution slows. The universe becomes a collection of lonely islands in an ever-growing sea of emptiness. If dark energy remains constant forever, this is the fate we expect. An eternally expanding universe that grows, colder, darker, and quieter with time. But this is not the only possible future. Because we do not yet understand dark energy's true nature, other outcomes remain possible. If dark energy weakens over time, gravity could regain control. Expansion could slow. In a distant future, the universe might stabilize or even begin to collapse. This would lead to a very different ending, sometimes called the Big Crunch. If dark energy grows stronger with time, the outcome could be even more dramatic. In some speculative models, acceleration becomes so extreme that it eventually tears apart galaxies, stars, planets, and even atoms. This scenario is known as the Big Rip. These ideas may sound extreme, but they're taken seriously because they follow logically from different possible behaviors of dark energy. That is why measuring dark energy precisely matters so much. Tiny changes in its behavior today translate into massive differences over trillions of years. Dark energy does not just affect distant galaxies, it affects the ultimate fate of everything that exists. This includes us, even if indirectly. Our galaxy will remain intact for a very long time. The Milky Way will merge with nearby galaxies. Stars will continue to shine. Life, if it exists elsewhere, will have time to evolve and flourish. But beyond those local scales, dark energy shapes the environment in which all future events unfold. It determines whether new galaxies can form. It determines whether cosmic structure continues to grow or freezes in place. It determines whether the universe remains dynamic or fades into silence. In that sense, dark energy is the background music of cosmic history. It does not dominate every scene, but it sets the tone of the ending. This realization adds emotional weight to what might otherwise feel like abstract physics. When scientists study dark energy, they're not just solving equations, they're trying to understand the future of reality itself. This also reframes Einstein's role in the story. When Albert Einstein wrote his equations, he could not have imagined that a small mathematical term would one day decide the fate of the universe. He was thinking about balance, not destiny, stillness, not acceleration, and yet his framework allows us to ask these questions at all. Dark energy reminds us that the universe is not static, not finished, not predictable in simple ways. It evolves, it surprises, it forces us to confront timescales far beyond human intuition. It also humbles us. Everything we care about exists in a brief cosmic moment, a moment when stars shine, galaxies glow, and complexity is possible. Dark energy tells us that this moment is temporary. That does not make it meaningless. It makes it precious. Understanding dark energy is not about despair, it is about perspective. It shows us where we stand in the grand timeline of the cosmos. It reminds us that the universe had a beginning and will have an end of some kind. And that end depends on a mystery we are only beginning to understand. When we step back from equations, telescopes, and cosmic timelines, the story of dark energy leaves us with something deeper than an answer. It leaves us with a lesson about how science actually works. Not the tidy version we learn in school, but the real one. Messy, human, unfinished. One of the most important things this story teaches us is that science is not about certainty. It never was. From the outside, science can look like a machine that steadily converts questions into facts. But from the inside, it feels very different. It feels like walking in fog with a compass that sometimes spins. Scientists work with partial information, limited tools, and assumptions shaped by their time. Certainty is rare. Doubt is constant. The history of dark energy makes this clear. For decades, scientists were confident the universe should slow down. Gravity made that conclusion feel obvious, reasonable, almost unavoidable. And yet the universe did not cooperate. Observation forced a revision, not because scientists were careless, but because nature had more to say. This is not a weakness of science, it is its strength. Science does not promise final answers. It promises a method for correcting itself. When reality disagrees, reality wins. This story also teaches us that even geniuses do not control outcomes. We often talk about science as if great thinkers shape reality with their ideas, but the truth is more humbling. Ideas do not command the universe. The universe judges ideas. No one understood this better than Albert Einstein. Einstein reshaped physics more than almost anyone in history. He changed how we understand space, time, gravity, and energy. Yet even he could not make the universe behave the way he expected. He preferred a calm, eternal cosmos. The equations he created refused to agree. What happened next is telling. Einstein did not abandon his theory. He adjusted it. Carefully, cautiously, he tried to reconcile his understanding with accepted belief. In doing so, he introduced an idea that later returned with a meaning he never intended. That is not failure. That is humanity. Einstein did not sit outside science as a mythic figure, delivering truth from above. He lived inside science. He made assumptions. He hesitated. He revised. He learned. This matters because we often tell the history of science as a story of right answers replacing wrong ones. In reality, it is a story of incomplete answers being reshaped by new evidence. Mistakes are not detours in science. They are part of the path. The cosmological constant is a perfect example. Introduced to solve one problem, discarded when it seemed unnecessary, revived when the universe demanded it. At each stage, scientists acted reasonably based on the information they had. Calling this a mistake misses the point. The idea survived because it was useful. It remained mathematically consistent. It stayed within a framework that continued to work. Sometimes, a so-called mistake is just an idea waiting for the right question. This is why questioning assumptions matters so much. Einstein assumed the universe should be static because everyone else did. That assumption felt natural. It was supported by limited observation and philosophical tradition. But assumptions shape what we are willing to accept from equations. When Einstein's equations suggested a changing universe, that suggestion felt too radical to trust. The assumption of stillness acted like a filter, muting a signal that was already there. This happens constantly in science. We do not see reality directly. We see it through the lens of our expectations. Progress often comes not from new data, but from realizing that an old assumption no longer makes sense. The discovery of dark energy forced exactly that kind of shift. It showed that even deeply reasonable expectations can be wrong. It reminded scientists that intuition, built on everyday experience, does not always apply to the cosmos. The universe operates on scales and principles that are not designed to feel comfortable to us. This story also teaches us something important about prediction. We often celebrate scientists for predicting phenomena before they are observed. That kind of foresight is impressive, but it is not the most common way science advances. More often, theories create space for possibilities that only become meaningful later. Einstein did not predict dark energy in the usual sense. He created a framework that allowed it to exist. When observation caught up, the framework was ready. This is how deep theories work. They are not instruction manuals. They are languages that can describe truths we have not yet learned to say. General relativity did not tell us that the universe would accelerate. It told us how space responds to energy. Once we discovered that empty space behaves like energy, the acceleration followed naturally. That is not prediction, it is preparedness. There is also a lesson here about humility. Science progresses not because scientists are always confident, but because they are willing to be corrected. Einstein accepted cosmic expansion when evidence appeared. He did not cling to the static universe forever. He changed his view. That willingness matters more than being right the first time. In popular culture, Einstein is often portrayed as a symbol of absolute genius. Hair wild, mind untouchable, answers pouring effortlessly from thought alone. That image is inspiring, but it is also misleading. The real Einstein struggled. He doubted, he argued, he resisted ideas that felt wrong to him. He held on to some beliefs longer than he should have, and let go of others sooner than expected. In other words, he was human. Seeing Einstein this way does not diminish his achievement, it strengthens it. It shows that science is not powered by superhumans. It is powered by curious, stubborn, thoughtful people who keep asking questions, even when the answers are uncomfortable. The story of dark energy also reminds us that science is always unfinished. Every time we think we are close to a complete picture, the universe introduces a new complication. Dark energy did not neatly fit into existing theories. It exposed a massive gap between our understanding of the very small and the very large. That gap is not a failure. It is an invitation to look deeper, to build better theories, to connect ideas that currently refuse to align. History suggests that such gaps are where the biggest breakthroughs happen. Newton's physics worked until it didn't. Classical mechanics worked until it couldn't explain atoms. Each crisis led to a revolution. Dark energy may represent the next one. And that brings us to the most important lesson of all. Science is not about controlling nature. It is about listening to it. The universe does not care about elegance, preference, or expectation. It reveals itself slowly, sometimes reluctantly, often in ways that force us to rethink what we thought we knew. Einstein listened more than most. Even when he resisted an idea, he never stopped engaging with it. His legacy is not just a set of equations, it is a way of thinking, a willingness to question even the deepest assumptions. The story of dark energy continues that tradition. We are still listening, still measuring, still unsure. And that uncertainty is not a flaw, it is the engine of discovery. In the end, this story does not belong to equations or telescopes or even to Albert Einstein. It belongs to the universe itself, a universe that quietly, patiently, and relentlessly refuses to behave the way we expect. Einstein once tried to freeze the universe in place, not because he lacked imagination, but because stillness felt natural, eternal, reasonable. The night sky looked calm, the stars seemed fixed. Change on a cosmic scale felt unnecessary, even unsettling. So he adjusted his equations, gently, carefully, to hold the universe still. And the universe moved anyway. It expanded, it evolved, it surprised. And when humanity finally noticed, the universe was already far ahead of us, carrying secrets that would take generations to uncover. That simple fact says more about reality than any equation ever could. The universe does not follow comfort. It does not care about preference. It does not slow down just because slowing down feels intuitive. It does not remain quiet just because silence seems elegant. The universe follows its own rules. Dark energy is perhaps the clearest reminder of this truth. It is not dramatic in the way explosions are dramatic. It does not announce itself with light or sound. It works silently, patiently, across billions of years, and yet it dominates everything. It pushes galaxies apart. It shapes the future of cosmic structure. It decides how the universe will age, cool, and fade, all while remaining invisible. That should humble us. For centuries, humanity believed the universe revolved around us. Then we learned Earth is not the center. Then we learned our galaxy is not unique. Then we learned even matter itself is only a small part of reality. Dark energy delivered the next blow to our pride. Most of the universe is something we do not understand. This is not an insult. It is an invitation to curiosity. Einstein's story teaches us that being right is not the highest goal in science. Understanding is. And understanding is not a destination. It is a process. Einstein was wrong about a static universe, but he was right about something far more important. He was right that reality is deeper than intuition. He was right that space and time are not passive. He was right that mathematics can reveal truths we are not ready to accept. And perhaps most importantly, he was right to keep asking questions, even when the answers were uncomfortable. Dark energy now stands as a symbol of that discomfort. It tells us that empty space is not empty, that nothingness has structure, that the universe can accelerate without engines, push without force, and evolve without intention. We do not yet know what dark energy truly is. We do not know whether it will remain constant forever, or change in ways that rewrite cosmic destiny. We do not know whether it points to new particles, new dimensions, or a deeper theory beyond everything we currently understand. And that is okay. Science does not end with certainty. It lives in curiosity. Every generation inherits unanswered questions. The ones we solve give rise to new mysteries. The ones we fail to solve remind us that knowledge is not owned. It is earned, slowly, through patience and humility. The universe is smarter than us, not because it thinks, but because it exists without explanation. It does not need to justify itself. We are the ones trying to understand. When Einstein adjusted his equations, he did not fail. He participated in this long conversation with reality. When scientists later removed the cosmological constant, they did not fail either. And when it returned transformed into dark energy, that was not irony. It was progress. Progress rarely looks like a straight line. It looks like hesitation. It looks like revision. It looks like returning to old ideas with new eyes. The universe keeps teaching us the same lesson in different ways. Expect surprise, expect discomfort. Expect that your most trusted assumptions will eventually be questioned. Dark energy reminds us that humility is not optional in science. It is essential. We are studying a universe that existed long before us and will exist long after us. Our role is not to dominate it with answers, but to listen to it with care. And there is something deeply beautiful about that. The fact that a small species on a small planet can even ask these questions is extraordinary. The fact that we can trace the expansion of space, measure distant explosions, and debate the fate of the cosmos is not trivial. It is a triumph of curiosity. In the end, the most important outcome of this story is not whether Einstein accidentally predicted dark energy. That question will always have nuance, always have debate. The more important outcome is what this story does to us. It reminds us that certainty is temporary, that knowledge evolves, that mystery is not failure. It reminds us that the universe does not owe us clarity, and yet it offers clues anyway. And it invites us to keep going, to keep observing, to keep questioning, to keep wondering, because the universe is vast, strange, and endlessly surprising. And every time we think we understand it, it shows us that there is more. Not to discourage us, but to remind us why curiosity matters more than being right. The universe is moving. It always was, and it always will be. Our job is simply to follow, eyes open, minds humble, and questions ready. And that, perhaps, is the most beautiful ending of all.